Here's another question, an FRQ on acids and bases. Acids and bases are the key ingredient in AP chemistry. I mean, 20% of the questions are going to be on acids and bases if you include the multiple choice. And look at all the topics we got. We've got the Bronsted-Lowry's, we've got pH, POH, strong, weak, equilibria, buffers, titrations, pH, properties of buffers, and the Henderson-Hasselbalch equation. So you got to know your acid and base. It's complicated, but once you get everything together, it sort of makes sense. And when you get that making of sense, it seems to be easy, but it's not really. It's difficult. So let's hit this problem here. Here we've got a weak acid, hydrofluoric acid, HF. It's the only halogen that's a weak acid, and it reacts to make H+, H3O+, and fluoride ions, its conjugate base. It's got a Ka of 7.2 times 10 to the negative 4, like 1 times 10 to the negative 3 rounded off. So it's, in terms of weak acids, it's up there. So let's keep going. We've got hydrofluoric acid dissociating water, and they give us the equation. Very nice. This is the molecular equation. Now, we've gotten to the part here. We've already answered the questions A and B, where you find out what the H+ concentration pH is of a simple solution. But now they're going to mess things up. This is where it really becomes AP, where we have the acid and we are reacting it with some sodium hydroxide. I mean, that's a strong base, and so we've got this arrow. This isn't an equilibrium. This is a reaction. And we're going to get rid of some of this HF that's there, and we're going to be making fluoride ions as a result. Okay, now they give us the stuff here, a volume and a concentration of the sodium hydroxide. Okay, volume and concentration. We can get moles. And here we've got a volume and a concentration of our weak acid. The two that react. We have both reactants. We've got an arrow. It's stoichiometry. Calculate the millimoles of fluoride ions and HF remaining in the solution after the reaction. Okay, they said immediately after because they don't worry about the ionization afterwards, which is minimal anyway. So, well, okay, we've got a reaction. So, ice table time. You probably could do this. You could do this in your head if you're really, really slick on it, but let's be careful and use the ice chart. We've got our HF. We've got our OH minus. Our hydroxide. Forget about the sodiums. Those are spectators. Water is always going to be 55 molar. And there we've got our fluoride ions. So initially, well, you can see I did the calculation here already. Let me pull my calculator out and show you how I would have figured that out. Calculator. Okay, bring it over. Here it is. 25 mLs of sodium hydroxide times 0.5. Oh, half of it. Okay, that's going to be easy. There's my 12.5 millimoles. I multiplied milliliters times molar, so I get millimoles. Worth remembering, makes things a lot easier. Otherwise, you're going to have to change this to liter and then type in times 10 to the negative 3 here, which is a pain in the neck. So concentration times volume gives us moles. And if you're using milliliters, you get millimoles. Great. You really should have 3 significant digits here if you're going to be perfect, but I'm carrying it one more so that we don't have any rounding errors. All right, we've got that. Now also we've got we have 41.3 of 0.5 molar. Well, let me just store this as X. Here, store. Where's my store? There's my store button. Store as X. Okay, I want to remember that number because I'm going to do some subtraction with an ice chart, definitely. And this is what we got the most of, 41.3 times 0.5 again. Okay, so we're going to have more moles. We're going to have more moles of acid than we've got base. So our, maybe there's 0.5 in there, and it gives us 20.65. And then, there we go. Yeah, my 20.65, exactly. Now, in the ice chart, you're going to have the change. Well, this is a full reaction, so this 12.5 mLs, 5 millimoles, is going to react with some of this stuff. There's a limiting reactant. Now, this is the critical part. We lose some HF. There you can see it. And we make fluoride ions. We'd make some water too, but who cares? because like I say, water is going to stay about 55 molar. So in the end, at equilibrium or end ice chart, we're left with 8.15. Again, you could run that off to 8. Yeah, well, that's 3 sig figs, or 8.2 would be probably a better way of doing it. And this is 12.5 millimoles. That's what we've done. Calculate the number of millimoles of fluoride and HF remaining. And this makes sense. We had 25 mLs of base, but we had 41 mLs of our acid, both at the same concentration. So we have some leftover acid still in there, and the base is gone, and some fluoride ions. We've got ourselves a buffer solution. We've got some acid and its conjugate base. Oh, I shouldn't have put the plus here. That works anyway. Now, next, what are they going to ask us? Calculate the molar concentration of the fluoride. Well, concentration is moles over liters, or if you're clever, millimoles over milliliters, which I hope you are. So here we go. I'm going to take my millimoles right there and over my milliliters, and that gives me liters. So millimoles are just beautiful. Let me get my calculator out and see what the answer is going to be. Okay, 12.5. Hey, I stored that. That's X. There. That's the fluoride. Yep. Divided by, and then parentheses, 25, because it's now in a bigger solution. We had that 25 plus the 41.3. 41.3. So it's going to be, oh, wait a second, back. I didn't put that plus in. Plus 41.3. Double check my situation there. I probably don't have to put this parentheses in here. TI is pretty smart. Let's see if it accepts it or not. I'm curious. Yeah, I figured I was going to close that. And here's this concentration, 0.189 molar, because the millis cancel out. That sort of makes sense. We start off at 0.5, and now we're getting less than that because we don't have quite that much material, and it's been diluted. So here we go. Let's see if I wrote this down. Yeah, 3 significant figures is pretty good. 0.188 molar. Again, the millis cancel. This is great. This is pretty straightforward stoichiometry stuff. We really haven't gotten into acids and bases. This is where it gets scary. Calculate the pKa of the acid and the pH of the solution. Oh, okay. Well, let's see. Ka, we had a Ka up there. Yeah, there it is. 7.2 times 10 to the negative 4. So calculator, I'm going to change it into the P value. So I'm going to take the negative log, thank you, Sorensen, 7.2 times 10 to the, I can use that EE button, negative 4. Should be close to 3. I probably don't have to close the parentheses either. Oh, I better put the 4 in there, because that's close to 10 to the negative 3, so we should get 3 point something or other. There we go, 3.14. That's going to be our pKa. Important value. It comes in really, really handy, because the pKa is where, if you know the pKa, that's when the pH, that's when you have a equal concentration of hydrogen ion and base ion producing a pH. In other words, if you have an equal amount of your original acid and its conjugate base, the pH of that solution will be the pKa. In fact, that's what I'm going to bring up right here. I'm going to bring up the Henderson-Hasselbalch equation. Here it is. Here's a section from the equation sheet. They've got the Henderson-Hasselbalch, their version of it, with the plus log of the base over the acid. The pH is equal to the pKa, we just calculated that, plus the log of the concentration of base over the concentration of the acid. If they're the same, this becomes 1, and everybody knows the log of 1 is 0. pH equals pKa. You could solve the same thing here. you could solve for the H plus concentration, and these two cancel out. The Ka at the ideal buffer is equal to the H plus concentration. The pH is equal to the pKa. That makes sense. And there's our Henderson-Hasselbalch coming back again. But here, let me bring it up where we can see it. Here it is. pH is equal to the pKa plus log of the base over the acid. If you can't remember it, you're going to have to flip over to that equation sheet. But this is one that's worth remembering because you're going to use it. You're going to use it. Now, here we go. I've got my pH chart. I'm going to do an estimate. If you have a equal amount of acid and base, the pH is going to be about 3.14. So here we got our pH, almost 2. This is a pretty acidic solution. It's dangerous because hydrogen fluoride is a very, very nasty stuff. You don't want to work with it. Make sure that if they're doing some experiments, your lab partner works with the HF. It's nastily poisonous and insidious and unfortunately not curable if you get a bad spill. So right now, if we had an equal amount of acid, in other words, you had 1 mole of acid and 1 mole of the fluoride ion, its conjugate base, you'd have a pH of 3. Now let's see, what do we have? Let's go back to what we had here. We had 8 of acid and 12.5 of fluoride. So we got more base than we have acid. Well, logically, if when these two are equal have a pH of 3.14, if you happen to have more base, let me write that down. I've got right now my not my concentration, my amount of base is 12.5 millimoles, and our amount of acid is 8.15. So the base is outnumbering the acid. You got to think about acids and bases. So therefore, instead of having a pH of 3.14 when they're equal, if the base is going to be greater, then we better expect, let me get my arrow and get a color saying it's basic. Let me pick this. My guess is going to be, I'm going to guess there. I'm going to guess that this is going to become more basic than a 3.14 because the base outnumbers the acid here. Maybe not that much. Oops, I got a curve on this, and I'm going to move that over because it's a log change. So my guess is going to be 3.9, but we can calculate it. This is not going to be difficult. In fact, I'm going to grab my calculator, and here we go. Here's my try at it. We have our pKa. That's going to be 3. Come on. I'm not even do that. I'm going to go second function answer all the way out to that many value plus the log parentheses of 12.5, the base. This is going to be a positive log because our denominator is less than that, 8.15. So there's going to be a positive value, and we add that to there. Let's see what we get. How good was my guess? 3.32. All right, I'll make it 3.33. So let's see, I guessed, it's even further over here. It wasn't, this is a log value. And, logarithms, this ratio wasn't that great. So, yeah, they were not that far apart. I should have figured out it was going to be closer, but that's what I got my calculator for. 3.333. Oh, that's a great number. Okay, 3.33. Now for your purists who said, wait a second, this was concentration of base and acid. Well, the base and acid were in the same solution. They were in the same total number of mLs, a total of 66 mLs. So their liters would have canceled. One of the nice things about the Henderson-Hasselbalch is you really don't, when it's used, you can just go by moles of each. You got to be consistent. If you can do concentration, you do concentration, but you can do moles and moles. This is just the amount of base over the amount of acid. So you didn't have to worry. I mean, I could have had here 12.5 divided by 46 divided by 8.15 divided by 46, but that would have canceled. So keep your mind open and be sharp when you do your acids and bases.